Excited about doing their assignment? Has everybody decided what game it is they're going to implement? Okay, so with these kinds of assignments, it's sort of important to have a plan before you start coding. It can be fun to experiment with games, but you want to have a pretty good idea what it is you intend to do. So one of the things that I'm supposed to teach you about in this course is two-dimensional arrays. It would take about, 5 minutes to teach you that. People think it's a big deal. It's actually not so much, and especially not so much in Python. But a good example of two-dimensional arrays are images. And so today we'll look at dealing with images. So some things you can do with images. So what you'll learn about basically is a few things that are about image representations and the kind of operations you can do on images. So in Python, there's this Python image library, it's called, and there's a bunch of stuff in there. One of these is the image class, so it's one of the more important ones, and so we'll look at that today. And while we're working with tkinter applications, and so when you want to display these images in tkinter, you use this image tk class /module. Okay. So I have in this directory we are the 31st. Happy Halloween. So in this directory, I have a couple of images. Oh, that's interesting. Doesn't matter. We'll see it in a second. There's a couple of images in here. So one of them is called lineage.jpg. It's a JPEG file. And the other one is called watermark.png. It's a PNG or portable network graphics file. So the first thing we'd like to do is open one of these things. So let's try lineage.jpg. So it's kind of obvious. Image.open opens the image and returns an image object to you. And maybe we'll get some information about it. So let's say width and height is equal to image.size at 0 and 1. I think that works. And let's print the width and height, just to see. So it's a 500 by 375 image, so it's 500 pixels wide, 375 pixels tall. So this is where these 2D arrays come from. We can index these images, the individual pixels of this image, using integers that are between 0 and 499 and 0 and 374. So probably we would like to see what's in the image. So let's display it. So like I said, this image class is somehow different from tkinter. It's not really part of tkinter. So there's this interface between the two, and so this image tk class. And in there is a method called photo image that takes one of these images and converts them into something that tkinter can display. And now you can use these all over the place in tkinter once you have them. The easiest thing to do is create a label. And labels, remember, they have lots and lots of different possible parameters, and actually one of them is the image parameter. So rather than display text with a label, you can display an image. And maybe we'll lay this out with the grid layout manager. And let's say we'll try that. So there's the image displayed. It's a picture of three really handsome looking guys. So what have we done? Well, we created this image, and then we jumped through a few hoops, creating a different kind of image that's compatible with tkinter, and we use that as the image for a label, and that label is laid out in a grid layout, row 0, column 0. So far, so good? Good. Okay. So some of the things you might want to know if you're dealing with images is how they're represented. Anybody know how an image is represented? So there's images that are RGB, where for every pixel you specify the amount of red, the amount of green, and the amount of blue. Usually that's an integer between 0 and 255 for each of those. Any other representations of images? What's that? A bit. So for black and white images, you can use a single bit to represent each pixel. Either the pixel is black, 0, or it's white, 1. Anything else? So image files are actually usually compressed. They don't represent each pixel individually. They break them up into blocks and compress them. But this image library, once we open an image, it uncompresses whatever's in the file and makes this two-dimensional array. Yeah.
I'm getting an error saying no module name PIL.
Yeah, so you're running Windows or something else? Yeah, so you'll have to install whatever module you need for that. But you can just download it from, just search Python pill. And there's binaries ready to install under Windows. Okay. Any other representations of images? So let's see if so this is this representation you just talked about. So after opening this image, I converted it to black and white. So that's what this 1 means. It's where each pixel is represented by a single bit. It's either 0 or 1, 0 for black and white for 1. And of course, then you have to take whatever information you had in that image and convert it to black and white. This uses what's called a dithering algorithm to try and make different levels of things that look like gray that match the image. So it's not a bad conversion. Any other ones for black and white images? Yeah? Grayscale. So grayscale is, well, it's similar. There's only one value for each pixel, and it tells you how dark that pixel is. So 0 for black, all the way up to 255 for white, with shades of gray in between. And we can convert to grayscale this way. That's much better looking. So each pixel is one of these integers between 0 and 255. Okay. So grayscale is, we'll start with that because it's one of the easiest ones to understand. And so let's play around with this image maybe a bit. So we want the pixels. Well, let's actually make a copy of it to play around with so we can compare the two. And we'll go like this. We'll make a second image, which is a copy of the first. We want a copy, we just don't want to assign to it because we're going to end up changing it. We don't care about the width and the height. If it's a copy, it should be exactly the same. Image 2. If you don't make a copy, you'll modify the original one? Yes. If I just said image 2 equals image, then they'll both refer to the same image. Changes to image 2 will also be changes to image 1, or the original image. So let's see. Okay, so now we've got them in a 1x2 grid box. And first image, second image. So if we want to manipulate the image, we want to get its pixels. And that's done with a function called load. And just so you know where I'm getting all this from, there's plenty of documentation in the Python image library. Here's where you download it for Windows. Under Unixes, it's usually either already in the distribution or available as a package to install. And the image module is the one we're interested in. And it lists all the functions in that module. So we've been using open, and we've used copy so far. And this load method gives you a bunch of pixels. It actually gives you a two-dimensional array of pixels. So if we want to see how this array is laid out, let's actually change the picture somehow. So we'll make a rectangle or something. 20 to 40. 40. So is that X, Y. So let's say we want to draw a white rectangle. So what do we set the value of pixels to? What do we set each pixel to? To 1. So in a grayscale image, it's between 0 and 255. 0 is black, 255 is white. So we'll set it to 255 and see what that does to the resulting image. There it is. There's the rectangle we just created. So this actually tells you something. So we did this with x coordinates in the range 20 to 39, y coordinates in the range 20 to 39, and so that tells us that this top left corner must be the origin, right? Because this distance is the same as this distance. This is a 20 by 20 square, and so is this thing. So that the coordinates in these images start at the top left corner. So if you wanted now, you can procedurally make any image you want to. I mean, you can create an image. You can actually open a blank image, specify the size, and then draw on it exactly this way, doing whatever you want, drawing circles or whatever you like. Okay. And there's what you need to know about two-dimensional arrays. A two-dimensional array is an array that has, well, 2 dimensions. You index it using 2 coordinates instead of 1. Okay, so let's do, instead of something like this, let's change the whole image. So we'll range over the entire x-coordinates over the whole width of the image, y-coordinates over the whole height. Of course, this is not a very interesting transformation. If I just do this, I just get a white image on the right, paints the whole thing white. But I don't know, what kind of transformations can you do? Pick something. Something easy. So what's a common thing that happens when you take a picture with a camera and you're unhappy with it? Red eye, yeah, that's a little more complicated. Luckily, black and white or grayscale saves us from red eye images. So one common problem with things you take from a camera is that they're too light or they're too dark, right? So sometimes you want to you would like to lighten an image or darken it. So how would you lighten the image? How would you make it brighter? I mean, here we made it really bright. We made it pure white. Yeah. So we could try and do something like add 10 to each value.
But you'd have to do in this statement so it doesn't pass 55.
Yes.
Or does it?
But actually, you don't need to worry about it because in these images, if the value goes beyond 255, it's just 255. So it's just it'll just be white. If it goes less than 0, then it'll be 0. So it'll be just black. So let's try that. Is that noticeably brighter? No, not really. Maybe we should add 50. That noticeably brighter?
Yeah.
It's sort of washed out now, but certainly it's brighter on my screen. It's hard to tell for you guys from here anyway. Another option, or different things you can try, in fact let's make a third copy of this thing so we can experiment a little bit. So something else we can do rather than just adding something is we can multiply. So we could try multiplying by, I don't know, maybe 1.3. And then we get an image which is, at least looks brighter to me, and actually is a little bit better, right? Because the things that are black means that they have a pixel value of 0, they stay black. So 0 times 1.5 is still 0, whereas the things that are a little bit lighter, they're the ones that get lightened. So this, these black tuxedos don't turn gray in this transformation. So something else that people do, or you can do, is, well, actually there's a company that's been just recently sold for $1 billion based essentially on this. Anybody know what company I'm talking about? Instagram. So sold to Facebook for $1 billion. One of the tricks that they use is they add noise to images. So they actually want the image to look like it was taken with a bad old camera, so they add some noise. And so we could do that by, for example, adding a random value to each pixel. And then we get a noisy looking picture like that. So maybe that's a little too noisy. There, a little bit better. So now it looks like it was taken by a 1950s era Polaroid camera or something, rather than a modern digital camera. Okay. Something else you sometimes see in in pictures or in image processing is, for example, fades, where an image fades as it goes from left to right. So let's say we would like our image to go to be completely black. You know, it's the regular image starting at the left, but as we go to the right, it fades to black. How would we do that? So make an image fade from its regular intensity to black as it goes to the right. So where are the pixels on the right of the image? What do their x values look like? What's that? No, those are the ones on the left, right? So the top left corner is 0, 0. And so on the right side of the image, we're looking at large x values. So how do we express, I don't know, mathematically or some way, that we would like the image to be black when the x values are as large as possible? So what do we do to a pixel? What's that? So we would like to multiply it by 0 when the x value is as large as possible. So that would be something like the width of the image minus x is a number that basically goes to 0 as x becomes close to the width of the image, then this number goes to 0. And well, we would like this to be basically a number between 0 and 1, so we divide that by the width of the image. So let's see what that does. Yeah. So you see that result on the bottom, more or less faithful as we start on the left side, and then it fades to black as we reach the right. So that looks like a badly developed Polaroid image. In fact, we can put both of those together and get what looks like a really bad picture from the 1950s. Okay, so there's a lot of common things people do with images, so much so that there's a whole library devoted to them, these things, and that's there's a set of image filters that we could try. So let's take a look at a couple of those. There's a bunch that are built in: blur, contour, detail, edge enhance, emboss, find edges, and so on. So let's try one of those. So basically, you know, this is to deal with this pattern that there's a lot of things people want to constantly do. So they're constantly writing loops that look like this, where they change each pixel in the image or do something to each pixel, or maybe even groups of pixels. And these are built into here. So we can say filter, image filter, dot, I don't know, let's try and blur it. Does that look blurry? Yes? Okay, good. And there's one that's actually really, really useful for machine vision, actually, or computer vision, and that's the edge detector. It's not called edge detect, it's called find edges. So this actually makes a black and white image, and it's black almost everywhere and white where it thinks there's an edge. So what do you think an edge is? Yeah.
Where it's like a sudden change in 2 colors.
Yeah, so it's where there's a sudden transition between 2 colors. For example, the black of this vest and then the white of the collar is a sudden change. You know, the pale face and then the white teeth, there's a change there. And of course, you really see these edges in the sort of man-made things like this cupboard in the background. You know, this thing is white, and everywhere there's a crack in it, well, that means there's a little bit of shade, so a black thing, and you actually get all of these edges. So this is actually a really powerful primitive operation in computer vision, where you have computers that are, you know, taking pictures through a digital camera or taking video, and wanting to understand what it is they're looking at. And one of the first things they try and do is identify edges. And then one of the next things they try and do is identify corners. But that's for that you need a little bit more than just one image usually. Okay. Any of these other ones you would like to see, or any of these other ones you're curious about? No, nobody cares. Yeah. Sharpen. What does sharpen do? Let's see. So there's the sharpened image. Do you see a difference? Yes? No? Yeah. So it tries to well, actually, I suspect what it's doing is doing an edge detector, and where there are edges, it's actually heightening the difference, cleaning up the transition to make it as sharp as possible. So if you look, for example, just around the outline of you know, this arm against the background, that looks a little fuzzy, and here it really gets crisped up. So it does some kind of thresholding there where the transition goes sharply from dark gray to white. Any other ones people are curious about? No? good. There are a few things. Kernel is something you can learn about if you ever take a course on image processing or a course with an image processing component. There are also these filters, they call them. And what they do is they go through the image one pixel at a time, and then they look at a neighborhood around that pixel and take some function of that neighborhood. So for example, if the min filter takes the minimum value in that neighborhood, and by default it's a 3x3 square around the current pixel. So what do you think the result of that is on a grayscale image? What's the general, what does that do to the image? What's that? So there's not too many things that can happen to a grayscale image. It either gets brighter or it gets darker. Taking the min filter, taking the smallest valued pixel in a, let's say, a 5x5 neighborhood, what will that do to the image? Well, let's see. So it makes it, well, it looks to me like it makes it generally darker, and it also makes it kind of blurry or a little bit strange looking, right? And that's because anytime you have a really dark pixel, that pixel takes over its whole, a neighborhood of radius 5 around it. So you end up with these really strange looking pictures like this. And well, if you don't want it to be darker, you could do, for example, the median filter. So now the image isn't darker, it's about the same level of brightness. So it goes through these 25 pixels in a 5x5 neighborhood and takes the one with the median value, so the one that has the same number of values less than or greater than to it, and that's the one it uses, which results in this blurry looking thing, but it's not any darker or any brighter really. So detail gets lost typically by those kinds of filters. Okay, so that's black and white images. There's lots and lots you can do with them. In fact, a lot of image processing and machine learning things, the first thing they do is take a color image and turn it into black and white, because often they don't care about color. They can get what they need from black and white. But let's go back to our original image, which will load, and we'll make sure it's in RGB format, red, green, blue format, which means that this is not going to work anymore. So we can't do these operations. Let's comment all that out. Okay, so the built-in filters continue to work with any kind of image, including red, green, blue. But we'll have to be more careful with the stuff we do ourselves. So now each pixel in this image is a triple. So let's just grab each triple. Red value, a green value, and a blue value. So are any of you photographers?
Yeah.
Yes. So what's a common correction you need to make with with pictures that you've taken. Even if they are correctly exposed, there's another common problem.
Either red eye or like a little bit of blurriness kind of thing.
So you get blurriness, you get red eye, but a more classic. What's that? Color balance. So white balance they call it, but it's really more like red balance or blue balance. And crop, so those things. But you know, one of these, the one you mentioned, is the balance of colors. So sometimes you take a picture and it's indoors under fluorescent lights, and everybody kind of looks green. Their skin looks green, or you know, it's out under some other incandescent light, and everybody's skin is really red and blotchy. And so that's actually a problem with the levels of the different colors. So for example, so let's say that, you know, actually in this picture, at least the two of us whose skin should normally be white looks pretty red. So maybe there's too much red in this picture. So how do we correct that?
Reduce the red value.
So we want to reduce the red component. So we've seen there's sort of, you know, different ways of doing that. We can subtract from it, or we can divide it. Let's, I don't know, let's try something really wild. Let's divide by 2. Let's use what we know. So there we took a lot of red out of the image. We went maybe a little too far there. Suddenly everything looks green. And this is actually a surprising thing about these color models, is you get really unexpected results, right? So you remove red and now things look green. And that's actually why color or white balance in an image is called white, in image processing is called white balance, because you sort of know you've got it right when your whites really look white. So when they look like this green text, this green color, you've got it wrong. So your white balance is off. So maybe divided by 2 was too much. I don't know. Let's try 1.3 or something. So there, it's a little bit, I don't know, it's, you know, slightly different, and it's, I don't know, maybe better, maybe worse, or maybe the people in this picture were just very red in the face. It was a hot day, I guess. But definitely the redness in the faces went down. The whites maybe are a little off, and what's really strange is that this also has to do with the device you're displaying them on. So on my monitor, it actually looks a little bit better than on that projector. This is why we have professionals who work with these things, because it's not that simple. Okay. So we can we can adjust the white balance this way. How about something maybe a little more let's say we'll drop this median filter. What if we wanted to add noise again? we want to add noise to a RGB image. How would we do that? So I need a little more feedback from you guys. You guys understand what's happening? It's easy. It's just boring. Okay. So I mean, that's fair enough. If you're not interested in image processing, that's fine. At least you'll take away from this the this two-dimensional array aspect, which is, like I said, it's something you can learn in 5 minutes. So how do you add noise to an image that's represented as red, green, and blue? Yep.
Are you trying to add noise to the red, then to the green, then to the blue, or all even amounts?
We can try both ways and see what the result looks like. So let's add some noise. Individually to each component. And we can try a version that adds the same amount of noise to each component. Oops. That should have been image 3. All right, let's try that. So here's our two noised up images. The one on the left adds a random value to the red, the green, and the blue. Each one gets its own random value. The one on the right gets its one random value that gets added to all three of those. I don't know, is one noisier or less noisy than the other? The one on the right looks more noisy, and it also maybe is a little more faithful color-wise, because by adding the same amount to the red, the green, and the blue, we're basically just lightening or darkening the value that's there, not really changing its color. Whereas here, by adding different quantities, we're actually changing the color of the pixels. So we could see that, for example, if we well, if we only added noise to the red, that'll probably, yeah, looks, well, it's hard to say. Looks a little less noisy. You really see on the wall gets lighter and darker. And the other ones, it sort of evens out. Okay. Now, one of the really common things, and in fact one of the recipes for doing lots of things with images, is actually combining images. So this is something that's used, combining images gets used all over the place, including some of the best rendered 3D games use this idea of combining images when they're doing their rendering. So for example, Doom 3, which is now pretty old, created or introduced this whole notion of rendering an image by drawing the image, assuming that there was uniform light throughout it, creating another image that that actually captures where the shadows are in the image, and then overlaying the two to get a really beautiful 3D image in which shadows and in which shadows are really beautifully drawn. And so so knowing how to overlay images is a useful thing. So in fact, so useful that it's almost at the top of the image module. There's new, there's open, and then two methods, blend and composite, which combine images. So if we look at the documentation for blend, it takes image 1, it takes image 2, and then it takes a number called alpha, which tells you which fraction of the image should come from image 1 and which fraction should come from image 2. So let's play with that a bit. We'll do that with this last one. Maybe we'll leave image 3 alone. So we'll open a second image. We'll see what that is in a second. Make sure it's in the same color model, RGB. It probably is anyway. But we'll convert it just to make sure. And then we'll overlay these two images. And we'll do that using blend with this alpha value. So let's say we want image 4 and we want image 5, and let's try an alpha value of 0. Okay, so it's in this bottom right corner here. We overlaid these two images. The alpha value was 0, so we got nothing. The first image, right? Looks like an identical copy of the image on the top. So let's try an alpha value of 1. Now we get a completely different image. So that must be this other image that we loaded. In fact, it is. So it's just a white image with some text. So if 0 gives us the original image, the first image, 1 gives us the second image, well, we can try values in between, right? So we could go with maybe 0.5. And then we get an image like this, where each pixel is the average of the 2 pixels in the 2 images. So, one of the images is white almost everywhere. So one of the effects of that is that the whole image gets brightened because we're adding 255 to everything in the first image, and then dividing by 2. So we get that situation. And you see a little bit here in the text, in the one place where that image is not white. Well, there's actually some actual blending that happens here. So you can still see through the text in some sense to the image in the background. So this looks like it's supposed to be doing something like watermarking. So when you're when you're a photographer who cares a lot about your copyright, you often watermark your images like this so people don't just take them and use them elsewhere. But this is not a great watermarking procedure, and why not? Yep. Well, it's easy to, maybe it's easy to get rid of, I don't know, but there's a bigger problem than that. Yeah. Yeah, I mean the image looks terrible, right? The image is super super faded in some way. So that's not great. How could we make it less faded? So this is actually, you know, a little rough for a watermark. In fact, in this picture, the watermark looks like the main thing rather than the image. So what would we do to make it more image and less watermark? Yep.
Put the value closer to 0 because the 0 represents the first one, right?
Yeah. So we can try a value closer to 0, maybe 0.1. Little bit, that's better for the image, but there is still some fading that goes on. So the colors are still not faithful. The watermark is there, and that's probably about the level you'd want a watermark. It's just enough to let somebody know that, hey, this image came from somewhere else than whoever's showing it to you. But it's still not perfect. And one of the things, you know, if you care about your work, your photography, you don't want your image to change that much because of the watermark. You just want some stamp on it. And so this function that we've been using, blend, will never really be able to do that for us. So blend takes two images and some parameter, some numerical parameter alpha, and says alpha controls the fraction that comes from one image and the fraction that comes from the other image. But that's all alpha does. And so basically the images will, you know, you'll always get something that's a mixture of the two everywhere. And what do you want really to happen differently in a watermark like this? So think about these things. You've surely seen them before. What would you really like to be somehow different about this procedure? What shouldn't it change?
Well, we want to take all the background color out of the watermark, so make it so it's just the writing.
Yeah, so you would like it to be, you want the watermark to show up, but you don't want to affect parts of the image that are not even part of the watermark, right? So for example, the watermark is just some text that's in a little box down here. And, well, why should that have any effect on what happens up here? So what you really want is some way of saying, well, wherever there is text in the watermark, I want to mix the two images, but otherwise I want to take just the original value from the first image. So let's see, you know, how you do that, or the way you do that. And that's actually a really common procedure. It's called compositing. So there you actually have three images involved. One of them is the two images you want to draw, and a third one is what's called a mask, and it basically takes the place of this alpha value. And well, the problem with alpha is that alpha is the same for the whole picture. What we would like to do is say, well, where we want something from image 2, the watermark, well, we'd like an alpha value that's, I don't know, something there, 0.5 or so, or 0.3 or 0.1 even. But where there's nothing in the watermark, well, we just want image 1. So, for example, let's for example, for everything up here, you know, above the watermark, we would like it just to be an exact copy of the original image, and you know, everything below the watermark we'd like an exact copy, and it's really only where there's text in the watermark that we want some kind of blending to happen. So we need to create yet another image, because this takes 3 images. So what could we use as this mask image? So I have the original file, I have a watermark, and now I would like to set a mask that says only combine things where there's something in the watermark. So what could we use then as this mask image? Yep. So a picture of some solid color wherever there's writing in the original picture. Do we have a picture like that?
Well, we could do it, but we just make it delete all the pixels that don't have that are within a certain range of color.
Okay, so there's an idea. So where would we get that from?
Within the watermark, you mean delete the pixels that aren't within the range of the lighter colors.
Okay, good. So we'll open the watermark. And actually the watermark is, you know, it's red and white, but that's basically black and white. So we can convert it to a grayscale image. Okay? And your idea is to go through the watermark, and well, so what do we want? We'll look at this pixel. This pixel at xy is white. So for the white pixels, what do we want to do? What's that? We'll get rid of them, which means we want to use an alpha value that takes everything from the first image. So what's the alpha value that takes everything from the first image? So that's like 0 or 1. It's going to be 0 or 255. We'll try 0 and see if that works. Otherwise, we actually have an image in the watermark, or a pixel in the watermark that's not white. So what do we want to do now to combine this pixel with the image? So do we just take we could just say 255, we'll take the watermark, and we'll see how that goes. Image 5 and image 6. Okay, not quite what we wanted, right? We got We sort of inverted it maybe. So let's try and fix that. So one way to do that is to change the values that we're using, assigning to these pixels, but another way is to just change the arguments. So change the role of the first image and the second image to that function. Okay, so there's something. Not quite what we wanted yet. So it looks like we're getting a real faithful copy of the original image, except around here where we're getting something else. So what's happening here?
Taking the pixels like from around it, and then it's not deleting those ones because they're combined with the red.
Yeah, so it's, well, there's a couple of things. So one is we're getting pure red, which is not really what we wanted. We wanted something that sort of blended into the image. So we can maybe fix that. So if the pixel is not white, we won't use 255. We'll use something that still allows some of the other image in, maybe 25. So there we're getting a little bit better. Maybe we should have gone higher. You can hardly see the watermark. Let's go 100. Not bad. Still, though, the watermark is a little, there's something weird going on here. Does anybody know what the problem is? Yep. Yeah. So, so this picture is drawn using the text is drawn using something called anti-aliasing, which means when a part of the text crosses basically the border of a pixel, where it crosses through a pixel. So you have this pixel it's not really text and it's not really background. It's a bit of both. That pixel gets drawn as a combination of those two colors. So that's a technique called anti-aliasing. And it's what actually makes fonts and curves look good on every display. Just because displays have these square pixels and curves are supposed to look smooth. So it's a trick to trick your eye into thinking that there's really this smooth curve happening, even though it's drawn on this grid. But for us, what that means is there's not just two kinds of colors in our image. It's not just white and red, but and we were sort of relying on only having two colors. Here we check if the pixel is white, then we do something. Otherwise, we do something else. But really, there's something bigger going on. So it's not if it's pure white, but maybe if it's bigger than, I don't know, 200. So that means it's almost white. We'll take the original image. Otherwise, we'll mix the two. Yeah. So there we go. We've still got a little bit of that happening. But there we've got a decent combination. So, people happy with this? Almost. And we could try and go better. Maybe we could go to 150. So then it looks even better still. If you want more watermark and less image, you could take this up to 175. Now the watermark stands out more. Still mixed with the background, but it's a little more prominent. And I'll actually leave you with an exercise, which is understanding why this works. So there's an exercise for you. Try and figure out why that worked. And we'll leave it at there today. If you want to come ask me questions specific to your assignment, we can do that for the next 10 minutes or so.